Hey everyone, it's me Steve, and I am going to do a quick video on some lunar observations I made on the 1st of March 2018, which was a full moon phase. I only observed it for about 3 hours. I tried to get it as close to half-hour increments as I could. I used, you're going to see which each picture frame, basic information on it. Here's observation 1, just to go through it real quick. You see the date, you see the time. Now, I'm in Central Standard Time as of right now. Now, here you see UTC. UTC time is actually March 2nd, because it's 6 hours ahead of me. So, but I failed to divide that up. I should have done that, and I didn't do that. Phase, mount level, I used a leveled tripod with bubble level. The first observation was not leveled very well, but this is what you're looking at right now. This is the very first observation. My latitude, my longitude, about my calculated azimuth, which I got from dateandtime.com, and calculated attitude. I transferred it into the azimuth. I translated into quadrant for you because I use my Brunton compass to measure these by hand, and I'm getting better at it because there's my measured azimuth and measured altitude, which were handheld, and I took, just with my Brunton, measuring the position of the camera. That's more for my sake than anyone else's information. Camera, I used Sarah's Nikon D5300, and the photographer was me. Now, I'm going to take you real quick through the 7 observations. You can go back and look at them if you want, because you can see there's information on every one of them. Okay, and as you can see, some of the pictures are better than others. I did have to mess with the contrast and stuff like that. Now I'm going to do some comparative analysis here, but I only used ones where I got decent photos. And unfortunately, doing this with a full moon is it's really bright. So I plan on doing this again, maybe at a waning gibbous or a waxing gibbous, so you can see more features. But I wanted to get the entire thing just to show you something. Alright, now we're going to go back to observation 2. Here we're going to see the Grimaldi crater and the Tycho crater. That's where those arrows are pointing. It's just for your reference. Now the words are going to disappear, but they're still marked. Now we are going to go to observation number 4. Now position number 2 is still there, but it's ghosted a little bit. Now we're going to go to observation number 6, and it's ghosted. Position number 4 is ghosted a little. What do you notice as I'm tracking Tycho and Grimaldi craters? You notice it moves relative to my position. Okay, between observation 2 and 6, both features have rotated relative to our vantage point. This is not libration, I don't think. There is something, I will show you daily libration, but this isn't it. This is just an apparent rotation due to my latitude and the fact that the Earth is rotating and the moon is orbiting, above us. This wouldn't happen if the Earth wasn't rotating. This also happens with the sun, which I plan on getting a video when we get better filters. But as I've mentioned before, and I've shown you, when the moon's near the horizon, using Tycho crater, you can actually reliably get your latitude. But as the night progresses, you see this apparent rotation of the moon, and Tycho crater swings. Now, the moon was rising at this point, so the Tycho crater is moving from right to left to my vantage point, and would eventually set being left. But I only did, 7 observations. So I just took this and got from the center of the disk of the moon, from where I was looking at it. There's about a 26 degree difference between position number 2 and position number 6. Now, if you extend it, now this isn't anything relevant. I just wanted to show you the change in angle from the center of the moon from my perspective. Now, if I pulled this all the way up to where north on the moon would be, the angle would be about half of that, I believe, about 13 degrees. But there's something else I want to show you, too. Real quick, I calculated that difference in angle. That's how I did it, just so you can see. And why does this happen? Well, now, this is from Dial Moon, all right? Now, please read what's in red. But this happens because as the night progresses, as you can see, north is labeled, the yellow and red dot is my position. Previous to the slide, you're going to see the yellow dot with the angle is my present position. But as you can see, as you go through the night, Earth rotates, the moon moves in its orbit. All right? So, but that isn't all that happens. All right? Now, this is the Aristarchus crater. I believe that's how you pronounce it. I'm not sure. We're going to take observation number 2 and observation number 7 here. All right? The crater is visible in both. I didn't label it on observation 7. I'm sorry, but you can find it just by looking at this stuff. All right? Now we are going to circle Grimaldi crater, another crater nearby, and that previous crater I just showed you its location. Observation number 2 is in red. The circles in observation number 7 are in green. Now, my transparency here in observation number 7 is 55%. It's going to stay that, and I'm going to slowly move that over the disk of the moon of my observation 2. Okay, so what do you notice here? Well, obviously, since the moon has rotated apparently from my vantage point, they're offset. So let's rotate observation number 7, which is in the green box. So other than the rotational changes, you notice anything else? All right, let's rotate observation number 7 to fit over observation number 2. So we rotate it, and it's about 30 degrees counterclockwise. Notice they don't exactly line up. All right, so let's zoom in. All right, here we are at 200% zoom in. Now, this is pretty matched up pretty good. The best I could do with my ability, and they're still not perfectly lined up. Why is that? Well, the green marked craters, observation number 7, have moved up slightly relative to the red marked observation number 2. This is due to our daily or diurnal libration. This is what allows us to see more than 50% of the moon. So does longitudinal and latitudinal libration as well, but you can't really observe that in a 3-hour period. So that's more over the entire year. So this allows, since we're looking at the moon at different angles throughout the night, we can actually see a little past the horizon than we could a few hours ago. And even during this 3-hour observation, it's noticeable here. All right, you can read this if you want. That's an explanation of daily libration from Wikipedia. But basically, as the moon moves across the sky, when it rises, I'm looking at it from a certain angle. Then as it moves, I'm looking at it from another angle, which I showed you, and then another angle, which allows me to see a little bit more on this one side throughout the night. All right, but I just wanted to show that to you all real quick and make a quick video of that. I plan on doing others, and I plan on doing I ordered a 6-inch moon globe, and I plan on actually doing an experiment setting it up to see, relative to my latitude, how this apparent swing moves throughout the night, then compare that to actual observation. But I need a clear night, and I need a night where I can stay up all night to do it. Because remember, there's only 2 true phases where, the full moon is out only during the night, except where it's right at the horizon, and the new moon is always out during the day, except for when it's right near the horizon. Now, throughout the other phases, the moon, as you move from full moon to new moon, the moon becomes more visible throughout the day. And it rises about 50 minutes, I think it is, later every day. And then when it starts moving away from a new moon to a full moon, it starts to be out less during the day. So we are going to make some more observations, but I think that's it for now. And if you have any questions or anything, leave them below, and I hope you learned something.